Okay, so we have just looked at the first 5 sections of the chapter, and I'm just going to take a peek back into the syllabus, make sure we're on task for making sure we get on task for our exam schedules. It's week 9 and 3, exam 5. Yeah, so exam 5 is going to cover chapters 9, 10, and 11. I'm also seeing here that we really do need to, wrap up chapter 9 today. So I'm going to go ahead and do that. We'll cover chapter 10 next week. We'll cover chapter 11 in week 11, and that'll have you ready for exam 5. So exam 5, we'll cover chapters 9, 10, 11, kind of a long one. Also, this is the time to be knocking out that summary 3. It's it's sort of due now, so please have that turned in by Tuesday. From what I heard, it sounds like a few people hadn't really started, so it sounds like you're going to be busy still getting data and knocking that out. But I'd like to see that turned in by Tuesday, please. Okay, let's roll on through the rest of the chapter here. So large-scale generation, 4-gigawatt Drax power station in North Yorkshire. And you can see that obviously any of these guys are going to need big cooling towers, lots of excess heat, and if you remember your Carnot cycle, 60% of the energy never leaves the station. Kind of weird, but where does it go? There it is, making hot water, making the atmosphere hotter. Okay, hydroelectric, a little more efficient, but obviously some environmental impacts. This is the Hoover Dam. If you've never been there, I suggest going. It's a pretty neat thing. You can actually go right down into the turbine rooms and see them. It's very, very neat, very clean, and it's fun to check out. Okay, now, how do we make the electricity? Well, various ways. Coal, obviously the big black king in the middle. We started off talking about king coal. That's why it's king coal. Oil was popular for a while. Natural gas has come online, and obviously nuclear, and now we can see the renewables and the waste sort of coming online. If you want to get really philosophical about it, all this coal is also waste. It's plant waste, really old plant waste. And when we get into 102, we'll see how Shramsky talks about that. Yeah, the oil was also waste, so was the natural gas. The nuclear, sure, I guess nuclear waste scattered throughout the planet that we concentrate and turn into fuel. But so, and on another philosophical note, I mean, it's all waste and none of it's waste. I mean, it's just a matter of turning it into something valuable for society. Okay. So CCGT, combined cycle gas turbine. So the Carnot efficiency is only as efficient as the difference in the temperatures. And what it says here, a conventional steam turbine can operate with outlet temperatures of 25 C or less, and the input temperature is as high as 600 C. Yet, as described in Chapter 8, combustion temperatures can reach 1300. This is only limited by the properties of the latest metal alloys. You can't melt your engine, obviously. Designing a single heat engine that could operate between a very wide range of temperatures can be done using a combined cycle with 2 separate stages. So what does that look like? So you've got one combustion chamber, air's coming into a compressor. These are all on a single shaft. So when the compressed air comes in, it's coming in such a way that the molecules obviously are closer together and have greater access to the gas coming in. Here comes your hot gas. The expander turbine is spinning as these hot gases flow through. These exhaust gases, which are still quite high, high enough to still boil water. Here comes your steam, your boiling water coming in, and now you've got a steam turbine. So one's just dealing with the combustion gases, the other's the steam turbine. Depending on the operating conditions, you can clutch this on or off, and out comes your electricity to the grid. And the reason for the word cycle is this water is just going through a hot and cold cycle, and as it's coming through, obviously there's some flue gases that are preheating the water to come through. So pretty clever, getting a kind of a 2-for-1 on the system. And it says the overall electricity generation can be as great as 50%. So better than that 30% that we typically get from the old school coal-fired power plants. Okay, the dash for gas, and I was just at the Department of Energy, and one thing that Jonathan Pershing suggested to me is that we take our biofilter reactor, and rather than try to scrub up all the nasty gases coming off a coal-fired power plant, that we actually apply it to a steam turbine plant. So we actually just put our biofilter on this guy, and then it's just sort of more or less eating CO2. So natural gas, if it's just pure methane, the only gaseous exhaust is pure CO2. So the chemistry becomes a little simpler. All right. So you can see, so 1990 is on the left, 2010 is on the right, and that this figure sort of reemphasizes what we saw before with gas coming online big time in the late to mid 90s. Okay, UK electricity demand and CO2 emissions from power stations. So with gas coming online, the emissions can go down, the electricity demand is going up, and again, it's kind of that logarithmic curve that we were seeing previously. Oh, and just to emphasize this, table 9.4 shows us that gas on a per kilowatt basis has about half the emissions that coal does. Nuclear, obviously, very small by comparison because it's not based on combustion. But gas on a CO2 per kilowatt hour basis, 452 grams per kilowatt hour versus 915 for coal. Okay. Now, small scale combined heat and power. So what we're looking at here is something where, rather than having this big old power plant somewhere way off, away from population centers, if you can burn your fuel cleanly and not end up with a bunch of poisonous gases where people need to live, you might build something like this, a combined heat and power. So this is what it looks like physically. So you still have combustion happening, but what you're able to do is take the heat and use it for something useful. So as I mentioned previously, with the giant systems, 65% of your energy is just lost as heat, only 35% of electricity. But with a small scale combined heat and power, here comes your electricity, here comes your heat with much smaller so-called losses. I would love to see something like this hooked up to our sewer system. So you take the sewer system, cap it so that it's airtight, and now somebody who's down here in the valley taking a hot shower or running their furnace or whatever, all those exhaust gases go into the sewer, and then I'm sitting up there in the rattlesnake benefiting from all the nice waste heat that's being made in the valley. I would love to engineer something like that. Obviously, you got to cap the thing so that you're getting better flows, and you wouldn't want a situation where you've got like a bunch of methane building up and you get a bomb or whatnot. But I think that's where our civilization is going. It's becoming more efficient, more local. So I could see, something like this, sitting down at a school, at a hospital, and then the waste heat just sort of flows, rather than up out a stack on a building, it sort of flows through the sewer system and then can be used in other parts of town. So anyway, call me when you're ready for me to design that. I'd be happy to do so. Just 2 hours listening out there. Okay. All right, so here's district heating. So this is gas fueled combined heating, and what you're seeing is this is something that's downtown. It's right next to apartment buildings that need heat anyway, and good use of keeping local waste resources local. Okay, 9.7. Now we're talking about transmission and distribution. So getting electricity out there. Here's a tower, 100 kilovolt, crossing the River Thames at Dartford. Here's another shot showing that unbeknownst to the passengers on this boat, you've got 275 kilovolt wires running right beneath their feet. Here's kind of a schematic of what our grid looks like, and I was showing this earlier: kinetic energy, mechanical, electrical, transformer, 25,000 up to 400,000 volts at the generation site, so you can actually push those electrons all the way out to the 200, 230 volt supplies. Wind turbines coming online. You got a little bit of solar. You got a little bit of solar thermal. Some combined heat and power, so it's a brave new world out there. So here's a shot of what the grid looks like in the UK, and this is inevitable. If you've got we talked, well, what we will talk about in 102 is say somebody's down here and they've put in a hydro barrage, and they've got way more electricity than they need. This guy's over here, freezing, or he needs to pump out his basement because some, waves just came over. How do you get it? Well, yep, you send it through the grid. So anyway, I would love to see a video of the whole planet sort of becoming this networked grid type thing, because it's pretty fascinating to watch. Yeah, and I don't know, and it'd be great to see also if this Netherlands, well, I guess it says it opened in 2011. It'd be great to see if this Norway connection happens or not. All right. Another thing, I think this will be about all we have time for, but on page 336 or 366, this says what exactly is being optimized. So we talked a little bit about combined heat and power and sort of milking as much heat out of that as you want. So it says, to a deep green environmentalist, such an optimization of the system might mean supplying adequate energy services such as lighting, heating, etc., using electricity system, but involving appropriate levels of electricity conservation and distribution of waste heat, as well as actual electricity supply. The whole system would need to be run to minimize pollution, but doing so at a reasonable financial cost. And some people fall in that category. At the other extreme, perhaps, a dedicated free marketer might see this as all too complicated. Electricity is simply a product, and the aim is to maximize sales at a minimum cost while obeying any pollution markets. In the middle, there's a long-term, so just make it cheap, make it dirty, doesn't matter. In the middle, there's a long history of state involvement in the UK and elsewhere. A cheap and reliable supply of electricity is seen as something essential for the growth of an economy. Obviously, if you want to bring in manufacturing, you need to run the motors. Yet, it may be something too important to leave to the free market, especially when fuel supplies, if they're coal, oil, gas, run short. Technologies such as nuclear power may require large amounts of finance that only the state is likely to be willing to provide. New technologies such as renewables may need subsidies, and we've seen some of that. Optimizing the running of such a system requires taking account not just the fuel costs, capital costs, expenditures, blah, 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 but also wider notions. So, really at the end of the day, what they're talking about is the economic growth. And if you get a chance, I encourage you to read this book. I took a quote from it. And I think, in fact, I still have it up here. John Brandenburg wrote a book called Dead Mars, Dying Earth. And if you haven't seen it, you've probably seen Al Gore up there going, do you want a bunch of gold or do you want the planet? You have to sort of choose one. So what we're talking about in terms of optimization is sort of making that choice. And what Brandenburg said is really, our economy comes from the environment. It comes from extracting resources from the environment, purifying them, transforming them, and selling them. At some point, the natural resources run out or are overexploited, and then you have the potential to collapse, not only the economy, because it's difficult to keep commerce moving, but and perhaps the collapse of the environment as well. So I think that's really the position that we're finding ourselves in, is how do you make a balance between the two? So that third paragraph that I just read. Okay, so it's a little over time here. I don't think we really missed a whole heck of a lot that's not too obvious. It's just kind of, I do love it here though, where they show that when the soccer game got hot, everyone's TVs turned back on, and I don't know, maybe the beer tap started flowing and the fridges had to come on, but they're showing how, society can drive that. Here's a smart meter where I think our electric grid's going to go. So we're optimizing supply and demand. A couple big power stations and globally. Okay, well I think we got through it there. Yeah, coal by wire. That's a big one. Yeah, it's a big chapter. But we'll pick it up next week with nuclear power and the next evolution in primary energy generation.